The standard history of mathematics often begins with a specific origin story. It follows a lineage of deductive proof that starts in ancient Greece, centering on the geometric diagrams and logic of thinkers like Euclid. This architecture treats truth as a chain of dependency. A mathematician starts with a set of definitions and postulates, then derives propositions until the result is a certified theorem. Relying strictly on formal proof to define mathematics leaves a gap in the historical record. Civilizations managed complex economies and monumental engineering projects for thousands of years without the use of Greek-style theorems. Roman surveyors turned measurement into physical infrastructure. They used right-angle construction and precise gradients to align hundreds of miles of roads and aqueducts. Here, mathematical reliability was established through institutional consequence and durable construction. Across the world, different cultures developed their own admissibility architectures. These are diverse systems for deciding which calculations are reliable and which methods can be trusted to govern reality. The Atlas of Reason is a map of these fragmented traditions. It reveals how diverse civilizations established their own unique ways of governing mathematical truth. One region of this atlas belongs to the calculators. In these traditions, mathematical truth is defined by the use of repeatable, authorized procedures and tables. Ancient Egyptian scribes practiced a problem-governed mathematics. They recorded worked examples on papyrus to solve administrative needs, from bread distribution to land measurement. Babylonian mathematics relied on numerical tables and sexagesimal computation. They stored computational commitments in clay, using ratios and reciprocals to create a reusable library of results. The ancient Chinese tradition was algorithmic. Truth was found in a specific sequence of rod movements on a counting board, transitioning from an input state to a verified output. This worked example culture provided an admissible path to a correct answer. It allowed a scribe to execute a calculation and arrive at a result that was actionable in the real world. For the procedural architecture, a calculation is true when the algorithm is authorized and the execution is reproducible. Other architectures belong to the builders. Here, mathematical reasoning is inseparable from the physical substrate and social space. The Inca used the quipu, a material ledger system made of knotted cords. The position and type of each knot functioned as a decimal database, allowing a vast empire to remember obligations and categories without a written script. In ancient North America, early earthwork traditions transformed pure geometry into durable landscape. Builders used surveying and measurement to create massive mounds and plazas, often aligning these social spaces with celestial cycles. In these traditions, the burden of proof is physical. A mathematical error leads to a failed building or a mismeasured field, a breakdown in the material order of the community. These mathematical structures are admitted into the culture when they are successfully built, gathered within, or materially recorded. The balancers represent a third architecture. This tradition focuses on the governance of unknown quantities and changing states. Al-Khwarizmi organized equations into classes, providing solution procedures that transformed unknown quantities. His methods used operations like aljab to repair and balance these hidden states until they were solved. This algebraic logic requires preserving an invariant relation. A mathematician can change the representation of the problem so long as the underlying equivalence remains intact. The Maya calendar provides an architecture for temporal state computation. It locates a specific point in time as a coordinate within interlocking planetary and ritual cycles, using a positional number system to track the deep past and future. In this system, truth is a governed transition. It allows a culture to locate the unknown or the future within a predictable, interlocking system of cycles. Powerful methods often outrun their own foundations. In the 17th century, Isaac Newton and Gottfried Wilhelm Leibniz developed the calculus of continuous change. This created a foundation debt. Calculus worked for physics and engineering, but its use of infinitesimals remained logically unstable for nearly 2 centuries. The 19th century saw a massive project of foundation repair. Mathematicians established rigorous definitions of limits and continuity, finally providing the explicit proof obligations calculus needed to be formally admissible. As mathematics expanded, it encountered new crises. George Cantor developed set theory to study the hierarchy of infinity, forcing mathematics to confront the risks of unrestricted set formation. Kurt Gödel provided the final proof boundary shock. He demonstrated that formal systems, strong enough for arithmetic, cannot prove their own consistency, exposing a permanent limit to what deduction can achieve. No mathematical tradition is a total, self-certifying origin of truth. Every system is a specific architecture with its own history, its own methods of admission, and its own boundaries. This governing question links the first prehistoric tally marks carved into bone to the modern algorithms of today. Each system provides a way to make calculation reliable. Understanding the architecture of a truth is the only way to recognize its limits.